Okay, now the next topic is going to be cardiac muscle and cardiac conduction, right? The cardiac muscle, cardiocytes or cardiomyocytes is the name of the cardiac cells. What characteristics do they have? They show striations, this one right here. Right, show intercalated discs. You have one right here, another one right here. It forms branches, as you can see right here. Forms branches. There's another branch in here. It has a big nucleus. And another one, it has a lot of mitochondria. Big mitochondria that will allow the cardiac cell to perform aerobic respiration. As you can see here in orange, you can see these are the mitochondria. The cardiac muscle is very susceptible to the lack of oxygen because if it doesn't have oxygen, they cannot produce ATP through aerobic respiration. Right here we have the branches. Right here you have intercalated discs. Intercalated disc has very important characteristics such as intercellular digitations and spaces. Right, these are digitations or folds. Right, there are spaces. There are desmosomes and gap junctions. The desmosomes and the gap junctions are going to fulfill very important functions. If you scroll down here, as I was saying, you have interdigitating folds, mechanical junctions, which are going to be the desmosomes, and you have the electrical junction that is provided to the cardiac muscle through the gap junctions. So right here we have the metabolism of the cardiac muscle, as I was saying. It contains big mitochondria and numerous mitochondria in order to produce ATP. Therefore, the lack of oxygen is very dangerous to the cardiac muscle. Then we have the conduction system of the heart. The conduction system is the electricity and everything that is associated with the electricity of the heart. So if we look at the heart, and we're just going to focus on the electricity, it's basically all this yellow part that you see right here, yellow, yellow, yellow that you see here, that's the electricity. So the first part of the conduction system of the heart is this area right here, which is called the sinoatrial node. It's called the sinoatrial node. It's called atrial because it's located right here in your atrium. This is the main battery, if we can call it like that, the heart is going to have. This initiates the electrical activity in your heart, and this electrical activity is going to get transmitted through the atriums to the second, let's say, battery that we have in our heart, which is this one right here. The second one is called the atrioventricular node because it's located between the atriums and the ventricles approximately. From there, you have a set of wires, basically, as you can see here in yellow, that are going to take that electricity down into the ventricles. And these are going to be called the AV bundles. The AV bundles go down through the interventricular septum, this one right here. And then the AV bundles are going to branch out into these little branches that you have right here that are going to go through the walls of the ventricle. These branches now are called the Purkinje fibers. What you have to understand is that the heart moves because the electricity of the heart makes it move. First is electricity in the heart, and then the heart moves. So you cannot separate the conduction system of the heart from the movement of the heart. If we scroll down, then obviously we're going to see the different components of the conduction system of the heart again. So number one, which is sinoatrial node. As we were saying, this is where the electricity in your heart starts. Therefore, it's usually called or referred as the pacemaker. Your heart beats more or less approximately 70 to 80 times per minute, and that is because that's the pace that the sinoatrial node is going to provide to your heart. Next one, we say the atrioventricular node. Then we have the atrioventricular bundles, and then we said the last part is going to be the Purkinje fibers. So the next part that we have is the nerve supply of the heart. We said that the heart beats approximately 70 to 80 times per minute. Some people faster, some people a little bit slower, but on average we can say 70 to 80 times per minute. However, you know that your heart can beat faster, for example, when you are running. Right? If you're running, maybe your heart rate goes to 110 times per minute. And when you are resting and you are sleeping, for example, your heart rate may go down from 70 to 60. So then that means that even though your heart has its own pace, then this pace that your heart has is modified by your nervous system. Since your heart is involuntary, that means that you don't have control over it. So that means that the nervous system that is going to control your heart is going to be the autonomic nervous system. The autonomic nervous system has two divisions, sympathetic and parasympathetic nervous system. The parasympathetic nervous system is the one that is going to make your heart beat slower. The sympathetic is the one that is going to make your heart beat faster. The next topic is the electrical and contractile activity of the heart. So if we scroll down, we have in here again the cardiac rhythm. We talk about the cardiac rhythm. We said that is provided by the sinus rhythm, the sinoatrial node rhythm. We know it as the pacemaker, as we said right here, say 70 to 80 times per minute on average. If you keep going down, we have the pacemaker physiology. In other words, the sinoatrial node. How the sinoatrial node is going to fulfill its job. Let's skip this part and let me bring you to something that you may be a little bit more familiar with, which is the impulse conduction to the myocardium. In this case, is how the electricity goes to the myocardium and how the myocardium, right, the cardiac muscle, actually works. This was covered in Anatomy 1, so you should be familiar with this. I'm not going to spend a lot of time in here. If you don't know this, then I would strongly recommend you to go back to your Anatomy 1 book and look at the electrical activity at the level of your skeletal muscle as well as the nervous system. You may have seen this line before, the red one, right, going up and going down. That's the one that you're going to have in the skeletal muscle. There is something called the action potential. So basically, this is the title for this thing would be the action potential. The action potential has two big pieces. It was one going up, depolarization, the one going down, repolarization. The beginning was the resting potential. So if we look in here, the resting potential in the conduction system is going to be negative 90 more or less. You receive an stimulus and sodium channels open. Sodium channels open, therefore they change the polarity from negative 90 all the way up more or less positive 30. So what makes this go up? Sodium going in. So what makes this go down? Potassium going out. How do you call this? Depolarization. How do you call this? Repolarization. How do you call the whole entire thing? Action potential. What happens then? What's the difference then between the cardiac muscle and the skeletal muscle? The difference would be that in the skeletal muscle, it just goes up and down immediately. In this case, there is a delay between when it goes up and when it goes down. This delay right here is something that you don't see in the skeletal muscle or in the nerves. So this delay right here is called the plateau. Sodium goes in, potassium goes out. What happens in here is that when the potassium is going out, calcium channels open right here in number 4 in the plateau. Potassium positive goes out and calcium positive goes in. So basically this remains flat because positive going out and positive going in will cancel out. So this delay right here is called the plateau. And as you can see here, that's number 4. Number 4, see here, it says calcium entering through slow calcium channels. So calcium goes in, potassium goes out, and that maintains this flat. Eventually all the calcium channels close, and then this potassium going out will trigger this part right here, number 5, that it goes down. So as you can see here, you see channels close, calcium, and then potassium keeps going out, which is going to determine this repolarization right here. So then the green represents the electricity in your heart. What happens after the electricity in the heart? Then you have the red, which is the cardiac contraction. The red line going down is going to be the heart relaxation. So going up, contraction, going down, relaxation. Why? Because the depolarization in green is related to the cardiac contraction. The repolarization in green is related to the myocardial relaxation. If we scroll up, we go back to this image right here. What we have seen so far is the electricity in your heart as well as how the heart contracts and relaxes. However, this figure right here shows you how the electrical activity is in the sinoatrial node, in the pacemaker. The pacemaker obviously does not stop, right? That's why your heart never stops either. Your heart is constantly beating. Why? Because the sinoatrial node is going to be sending information or depolarizing all the time. That happens because it's just more or less the same concept. You see the line going up and the line going down, going up, going down. So this one doesn't stop. We can say that basically the relaxation or the resting potential is negative 60. It goes up again because of sodium. Eventually calcium joins it, goes in, sends this up, depolarization. It goes down because again potassium comes out. It goes down to negative 60 and it starts over again, which is slow sodium channels open up to more or less negative 40. There, sodium and calcium channels open even more, and then this goes up immediately up to negative 10 more or less, and then it goes down again to negative 60 because potassium goes out. And this is going to represent the action potential.